Alrighty, guys, welcome back to class. Sorry for the slightly late start this morning. I had an extra meeting that ran a little bit late, but today is going to be a fun day for us. We're going to transition from talking about all of these different kinds of functions we've been studying into talking about systems of equations, which is going to lead us to the study of matrices and matrix algebra, a truly beautiful corner of the mathematical universe. What this really is kind of opening the door to a field of mathematics called linear algebra. And while I know you're all excited to take calculus, and that is everybody's next step here for the most part, if there's one kind of field of math that is used universally in every science, every engineering discipline, literally every technical discipline in the world, it's linear algebra, which is the thing that we're going to start talking about today. So while it is not necessarily a calculus thing, there are some applications within calculus, don't get me wrong. It's not a strictly calculus thing. It is an extremely useful thing. All right. Let's do the title card. This is MAC1140, section number 008, which is pre-calc. And today is the 23rd of November, 2021. Today, we're going to start talking about systems, specifically systems of linear equations. And this is going to be 10.1 and 10.2 kind of together if we can. Although today will be more focused on 10.1, and then Thursday, oh, we don't have class on Thursday, do we? All right, so video lecture on Thursday will be more focused on 10.2. I guess before we get into this, just a few little reminders. Please complete the Jello worksheet. ASAP. Remember, that is a necessary mandatory thing. Used to be assessed on the final, but now it's a way for you to earn some points back on your last exam, or not your last exam, on exam 2. So please, the sooner you can get that done, the sooner I can give you those points. And also, it's statistics that the department needs desperately. Just make sure you follow the instructions. Specifically, please print the worksheet out or do it digitally. Don't handwrite the questions on paper. And make sure you solve the problems 100% genuinely on your own. Very, very important, those two things. So the other little reminder here, there is a new homework set up. WebAssign. And I'll try to get through 10.2 today, but probably today, like I said, mostly focused on 10.1. So for the 10.2 content, since you guys are a Tuesday, Thursday class, you're going to lose the second lecture this week again. I'll post a video lecture for you, so you make sure to watch for that. And that lecture may also introduce some of the 10.3 stuff. I don't think we're going to need a full day for 10.2, especially what we're going to do today. So yeah, these things keep in mind. Please knock out that Jello worksheet as soon as you can. There's a homework set that I'm opening up for you today, and it's going to be due a week from today, next Tuesday. But there will also be new stuff coming down the pipe. So please don't delay on this just because I'm not making it due on Thursday. The holiday definitely throws a wrench in the system, especially with Veterans Day having just happened. So we need to be careful with our time management and stay on top of things. I think that's about it. We did the makeup session for exam 3 yesterday. If you haven't taken the exam, for whatever reason, please reach out to me. Even though the makeup session has passed, I don't want anybody to be sitting with a 0 in an exam spot. So if for whatever reason you haven't taken it, since we are now a week past the date, we would need to talk about what happened. But I would like to talk to you about it and see if we can get it done. No, so I'm not going. This homework isn't going to be due on Thursday. But depending on the content of that video lecture, if we get into 10.3, which is a little bit matrices stuff, I may post a new homework for you on Thursday, or corresponding to the lecture that would normally have been on Thursday, the video lecture. But it kind of depends on what feels right based on where you guys are and how much we get through today. So let's get into it. So a system of equations equations is just a collection of equations meant to be solved simultaneously. So I give you, maybe you've got like 3 variables and 3 equations, maybe 2 variables and 2 equations, or maybe 5 equations and 6 variables. So it's just a collection of equations, more than one equation, and it might have more than one variable in each equation. And the idea is you want to find the values of the variables that satisfy all of the equations at the same time. That's what we mean by simultaneously. Such a system is called linear if all the equations in it are linear equations. And what we mean by that is that the variables are upstairs only to the power of 1, linear, like the equation of a line, just generalized to multiple variables. Yes, Megan, the final will replace your lowest midterm test grade if the final is higher. So if you earn like a 75 on the final and your lowest test grade is a 60, then I will go back and replace that lowest test grade by whatever you earn on the final, the 75. Okay, so some examples. Here are some systems of equations. Some of these are linear, some of them are not linear. Let me change one thing here. Okay. Okay, so we're getting some other questions about the tests in chat here, so let me address these. If the final is lower than your lowest midterm exam, then I won't be changing anything, right? So then that grade is what you get on the final, but I won't go back and replace any of your tests by that. So if your final score is not better than any of your midterms, then I'm not going to go back and replace one of the midterms. Basically, we only do this if it helps, right? We replace your lowest midterm by the final if it helps, if it brings your grade up. And then if you want to talk after class, I think I have another class right after this one, so I don't really have time to chat after class for more than like 2 or 3 minutes. If you want to, if it's a quick thing, we can do that. Otherwise, it's going to have to be an office hour thing. But yeah, just hang out towards the end, remind me that you want to talk, and we can do that. So what I'd like to do is classify each of these systems as linear or nonlinear. So let's start with this first system here, x plus y equals 0 and 2x minus y equals 3. Is x plus y equals 0 a linear equation?
Yes.
This equation, just this equation, x plus y equals 0, is that a linear equation?
It is, isn't it?
I don't think you can hear us.
And other issues,
Oh, sorry.
non-monetary issues.
The radio playing still. Well, the graph of this equation, this is the same as y equals negative x, right? And that is a straight line. Yeah, sorry about that. Sorry, I had my volume down because the radio was on. I forgot. I'm sorry. So the answer there was what? Linear?
Well, I mentioned that the economy as it stands
What?
now
I
is
paused you.
clearly
Go
very
away.
different from how it looked when Powell started in 20.
There we go. What? Sorry. So this is linear, right?
Yeah.
Both of these equations are linear. So this is a linear system. And I would classify this as a 2 by 2 system. So it's got 2 variables. Oh, sorry, we'll say it like this: 2 equations and 2 variables. And we call that a 2 by 2 system. So this is a 2 by 2 system of linear equations, or a linear 2 by 2 system. The first number is the number of equations. 2 equations, that's that first number, and 2 variables. That's that second number. All right, what about the second system here? E to the x minus y equals 2 and negative x plus the square root of 2 times y equals 0. Is that linear or not?
Isn't it not linear?
Good, yeah, this is nonlinear. Because of the e to the x. And this is still a 2 by 2. Because there are 2 equations and 2 variables, x and y. Is the square root of 2 here a problem? Is the second equation linear or not?
Isn't it nonlinear still?
So certainly the whole system is nonlinear because the first equation is nonlinear, right? We only call a system linear if all the equations are linear. And since the first equation is nonlinear, the whole system we would say is nonlinear. But specifically the second equation, is that a linear equation?
Wasn't it linear?
Yeah, the second equation is linear. So the negative x plus the square root of 2 times y equals 0. That is a linear equation because the y is not underneath the square root. All right, I just put a little tail there to make that extra clear. So some constant times x plus some constant times y equals 0. That's definitely a linear equation because the y isn't being raised to any weird powers. He's not underneath the square root. This would be a straight line, right? The graph of this would be a straight line whose slope is 1 over root 2. And if you're unsure, you can always graph the thing. There it is, right? This is indeed a linear equation. The graph is a straight line. So the whole system is nonlinear because of that guy. But this equation, this is a linear equation. So sometimes we get in the habit of seeing a square root and automatically saying nonlinear. But you need to be careful. A constant under a square root isn't a problem. A variable under a square root would be a problem. All right. What about this third system? I've got 4 squared.
It's non-linear.
So let's look carefully. I know that there's some things in here that are meant to kind of throw us off a little bit, and definitely seeing this power might make us think nonlinear, seeing the square root might make us think nonlinear, but think carefully about the definition up here. Are all the variables upstairs, and are all the variables occurring only to the power of 1? Let's see, I've got 4 squared times x. Well, that's just 16x, right? 4 squared is a constant. So I've got 16x minus 3y equals 1. That is a linear equation. And I've got x plus the square root of 2 times y equals 3. This actually is linear. This is a linear 2x2 system. So as long as there's nothing weird being done to the variables, as long as the variables aren't being raised to a weird power, the variables aren't under the square root, then we're okay. This first guy would be a line whose slope is 16 over 3 and whose y-intercept is -1/3. You can put this into y equals mx plus b and verify that he is actually a linear equation. And the second equation, this would be a line whose slope is -1 over root 2 and whose y-intercept is 3 over root 2. So the first system and the last system on the left here are both linear. The middle system is nonlinear, but not because of the square root, because of the e to the x. This guy, definitely nonlinear, right? Because of this and this. The second equation is linear, but the first equation is not. And this is also a 2x2. Two equations, that's the first number, and 2 variables. What about the third guy? Is this system linear or nonlinear?
Wouldn't that also be linear?
Yeah, this one is linear, right? Everywhere you see a variable, it's just being raised to the power of 1. It's not downstairs in a fraction. It's not under a root. It's not in an exponent. And that's true in all 3 of these equations. So all 3 of these equations are linear equations in each one of their variables. So this would be a linear 3x3 system. And just to make sure we're comfy with the naming scheme, let's look at an underdetermined system like 2x minus y equals 0, x plus 3y equals 1, and negative x plus y equals 7. Is this last system down here linear or nonlinear?
Linear as well.
How would you describe the dimension here? So this is a linear system. How many equations do we have?
3.
Good. So this is a 3 by something. What's the something? How many variables do we have?
2.
2. So this is a linear 3x2 system. So the first number is the number of equations. The second number is the number of variables. A system where you have more equations than you do variables is called an overdetermined system. A system where you have more variables than you have equations is called an underdetermined system. Most of the systems we're going to look at will be what we call square systems, where the number of variables is the same as the number of equations. You can think of the equations as like constraints or restrictions, and you can think of the variables as degrees of freedom. And in a very real way, when you first start learning about what dimensionality is, this is where you start. So we would say that this is a two-dimensional linear system. But that's just terminology, not an important thing. What we do need to know is that we need to be able to determine whether a system is linear or not. And we need to know how to write down the dimension of the system, 2 by 2, 3 by 3, 3 by 2, so on. We are going to focus on linear systems. Nonlinear systems are hard. And when I say hard to solve, I don't mean just like unpleasant. I mean like most of the time impossible. Even if a solution exists, most of the time it's impossible to solve the system. In fact, it's often difficult to even figure out if a solution exists to a nonlinear system. Linear systems I don't want to say they're easy, but they're nice. We know pretty much everything there is to know. We can solve these readily when solutions exist. And we can tell. When solutions exist. So nonlinear systems, sometimes you can solve them using substitution. But for the most part, if you write down an arbitrary nonlinear system, like the ones I wrote down there without thinking about it too hard, only one of those that I wrote down do I know how to solve. Of the two nonlinear systems there, only one of them is solvable in any reasonable way. The second one, the one with the e to the x, is incredibly hard to solve. So our focus will be on linear systems. And the methods for solving, so we to solve these, there are three methods. The first one that your book discusses calls the graphical method, and I'm gonna give these to you in the order from like the shittiest to the least shitty. The graphical method is I wouldn't even call it a method, honestly, but your textbook does, and you know, I have to introduce you to the terminology in the book. First method, graphically. This is where you sketch the graphs of each equation. And find the point or points where the graphs touch. Now I think it's pretty clear why this is not a great method, unless that point is a nice integer coordinate point. It can be very hard to tell just by looking at the graph. Even if the coordinates of the point are integers, if we're being honest, you know, it can still be quite hard to see sometimes. So the graphical method really doesn't even deserve to be called a method. But thinking about the systems graphically can be useful in some other ways, classification and stuff. So this is one somewhat viable approach. Graph the equations and then see if those graphs touch each other. If they do touch each other, can you tell exactly where? If yes, then that point will be the solution to the system. The second one is one you're probably familiar with from high school. This is called substitution. Substitution is where you solve one equation for one variable. Like maybe you solve the first equation for y. Then you plug that into the other equation or other equations. And try to solve for the remaining variables. If it's a 2x2, then there'll only be one variable after you plug that in. If it's a 3x3 or higher, then you'll have multiple variables left and you'll have to continue working. Substitution works okay for 2x2s. Graphical method really doesn't even work for most 2x2s. This just kind of sucks. But for any 2x2, you can solve reasonably quickly using substitution. However, for a 3x3 or larger system, you really don't want to use substitution. It takes forever and it's so easy to make mistakes. So the Mac Daddy here, and I will require you to learn this, is elimination. This is where you perform row operations. And I'll describe those row operations to you. To get rid of all but one variable in one of the equations. Then solve for that variable. And back substitute. So say you've got a 2x2 system, you do some row operations, you get rid of the y's in the second equation. No more y's, you just have x's. You solve for x. Now you have x equals some number. And then you would plug that number back into one of the other equations to find y. That's called back substituting. And again, there might be multiple other variables that you're working on. So I want to say again, the first two, this is graphical, this really sucks. Substitution, this kind of sucks. It's okay for 2x2s. Elimination, this is the good one. Works for everything. And elimination is how we're going to start working with matrices, which is a big deal. So you really need to learn elimination. I will do a couple examples here where we look at the graphical approach and we look at a substitution approach, but the remainder of the time in chapter 10, we will be working with elimination. Okay. So let's take ourselves a nice 2x2 linear system and try to solve it graphically. We'll come up with a guess using the graphical method, and then we'll verify that guess using the substitution method. And then from there on, we're going to work with elimination. I'll give you a second, make sure you've got these down nice and clear in your notes. I will say one thing before we leave here, substitution. This is the best approach for a nonlinear system. If you have a nonlinear 2x2 system, most of the time when we can solve those, we solve them with substitution. But again, nonlinear systems generally are hard as shit, and we really don't care that much about them. Okay. So let's estimate the solution to the linear system 2x minus y equals 5 and x plus 4y equals 7 using the graphical method. Now that first equation there, I'm going to call this equation 1. And the second one I'm going to call equation 2, because I'm going to have to refer to them. Graphical method says graph both equations. So, okay, I want to graph equation 1 and graph equation 2, and then try to see where they touch. So equation 1, let me put this into y equals mx plus b. 2x minus y equals 5. That's the same as negative y equals negative 2x plus 5, subtracting 2x from both sides. And then dividing both sides and multiplying both sides by negative 1, I get y equals 2x minus 5. Okay, so that's a nice form to graph equation 1. Let's do the same thing with equation 2. Got x plus 4y equals 7. So that's the same as 4y equals negative x plus 7. And that's the same as y equals negative 1/4 x plus 7/4. Now I will sketch both of these. So here's my x-axis, here's my y-axis. And let me put these in different colors here. How about, I wish I had my orange. That's all right. 2x minus 5. So I'll come down here, 2, 3, 4, 5. There's that y-intercept. And I know his slope is 2. So if I go over 1, I go up 2. Over 1, up 2. Like this. So kind of modulo my bad art. There's the graph of equation 1. And equation 2, I will put in a dark blue here. That's negative 1/4 x plus 7/4. Now, how big is 7 over 4? Well, it's 1 3/4, right? 4 goes into 7 one time, and then there's 3 left over. So if I come up here is 1, 2, 3. 7/4 is just a little bigger, a little smaller than 2. And his slope is negative 1/4. So that means if I go over 4, I will go down 1. So 1, 2, 3, 4. So the next point there is this. Actually, no, it's not right because we're going down 1. Yeah, so it's going to be like here. something like this. That's equation 2. Not beautiful, but we can see that there is a solution, right? The solution is this ordered pair, the point right here. The ordered pair, the point where these touch. Now, here's y equals 1, right? And it looks like that y value is pretty close to 1. And here's x equals 1, 2, 3. So it looks like somewhere around 3, 1. But it's really hard to tell. As it's drawn, that x value looks to be a little bit bigger than 3. That y value looks to be pretty much exactly 1. But my graphs aren't perfect, right? I'm a human being drawing these graphs. I can't draw a perfectly straight line. And even if I could, I couldn't tell you for sure that that's what that point is. It just looks like it's close to that. So this is about as good as the graphical method can get. And you see what I mean when I say it, it kind of sucks. At best, I have a guess. So if I want to solve this, two x minus y equals 5 and x plus 4y equals 7 using substitution, then I can find out for sure what that point is. Maybe it is 3, 1, maybe it's something else. Just for fun, I mean, I did already solve both of these for y, so I could take this and plug it into the other equation. But let me, just for the sake of practice, let me solve the second equation for x, and I'll plug that into the first. I'm going to solve equation 2 for x. So you pick one equation and you solve it for one of its variables. It doesn't matter which equation or which variable. X plus 4y equals 7 is the same as saying x equals 7 minus 4y. Then I plug this into the other equation. So instead of 2x minus y equals 5, I'll have 2 times 7 minus 4y minus y equals 5. Right? X is 7 minus 4y, so 2x is 2 times 7 minus 4y, and you need those parentheses. Distributing the 2 and combining like terms, I get 14 minus 8y minus y equals 5. Negative 8y minus y is negative 9y. So that's the same as 14 minus 9y equals 5. And then I can subtract 14 from both sides. So I get negative 9y equals 5 minus 14, which is negative 9. So dividing both sides by negative 9, I get y is equal to 1. Okay. So the y value was 1. We were correct about that. Now, we plug y equals 1 into either original equation and solve for x. So if I take y equals 1 and I plug it in, again, it doesn't matter. Let's plug it into equation 1. I get 2x minus 1 equals 5, which means 2x equals 6, adding the 1. And that means x is 6 over 2, which is 3. So we were right. 3, 1 is the solution. All right, it's the ordered pair x, y, where x is 3 and y is 1. That's the point where those lines touch. We suspected that from the graphical solution, but we weren't sure. Any questions on what we did with either of these pieces? Okay. What I'd like to do now is show you how to solve a system by elimination. This is really the way to go. Substitution, like I said, okay for 2x2s, okay for nonlinear systems. But in general, when you're working with a linear system, you should pretty much always use elimination. I cannot think of a reason to ever use anything other than elimination. And that's the thing we mostly need to practice, because I know a lot of us get to this point without ever really learning the elimination method. And here, while we're working with small systems, 2x2s, you could get away with either. But in the next section, where we're working with 3x3s and larger, you need to use elimination. Trying to solve a 3x3 or a 4x4 by substitution will make you want to kill yourself. It's a terrible process. So let me describe to you the allowed row operations. So remember, we're going to do row ops. To eliminate a variable. And the row operations you're allowed to do, you can multiply through an equation, aka row. So I'm going to start using the word row to refer to an equation, right? Like this is row 1, this is row 2. By any non-zero constant. That is one of the allowed row operations. You can add any row to any other row. And the third row operation is really just combining the first two, but doing it all at once. You can add a multiple of one row to another row. So the idea is you start with this original system, and by doing some number of these things to that system, you arrive at a system where one of the equations only has one variable. And you solve that equation for that variable, and then you back substitute. So here, let me just start with the original system. 2x plus y equals 1, and 3x plus 4y equals 14. I've got a 2x here and a 3x here. I've got a 1y here and a 4y here. What I want to do is change the coefficients so that one of these is the negative of the coefficient in the other equation. So like if I could make this 2x a negative 3x, then I could add row 1 to row 2 and the x's would go away. If I could make this 1y a negative 4y, then when I add row 2 to row 1, the y's would go away. So my first row operation here, and I'll show you the notation. Let's say my new row 1 is going to be negative 4 times my old row 1. So big R for new row, little r for old row, new row 1. And this guy right here, the little r1 is old row 1. So the row operation I'm doing here is the first type. I'm going to multiply through the first row by negative 4. And that will give me a new system where the second equation is the same as it was before, 3x plus 4y equals 14. And the first equation now is going to be negative 4 times 2x, which is negative 8x. Negative 4 times y, which is negative 4y, equals negative 4 times 1, which is negative 4. Does everybody see the row operation that I did there? Oh, I almost forgot one. There is a fourth row operation you can do. You can also swap two rows. That won't be important here, but it will be important when we get into bigger systems. All right, so any questions about how I get this system from this system?
You can take whichever row that you want and then do that with, like you could have done, I mean, that works for, I mean, it doesn't matter which row you pick, or do you have to pick like the first row first?
No, what you said first is correct. You can do any of these things to any of the rows. And if you want to, right, whether I write this equation first or this equation first really doesn't matter. It's the same system. Yeah, I'm still looking for the intersection of those two graphs. So the position of the rows doesn't matter. So you can move the rows around. I could swap row 2 with row 1 if I wanted, and that would give me nothing new. I would still have the same system. There will be later, when we talk about bigger systems, I will give you a kind of very set algorithm to follow to solve, because those can get kind of complicated. But for now, when we're working with just a 2x2, things are, you can kind of see the whole picture all at once. So you don't really need to stress about the position of the rows.
And that's because you can add rows together, but you can't subtract them, right? So it doesn't matter which one comes first.
Mostly.
Like if you're using the adding rule.
Yeah, so adding 2 rows together doesn't matter which one comes first. If you think about this guy, the third row operation, adding a multiple of one row to another row, this says you can subtract rows. Because if I multiply a row by -1 and add it to the other row, that's the same as subtracting that first row from the second row. So subtracting rows is an implied operation here, but we usually don't think of it as its own thing. We think of it as a special case of this third one.
Okay.
So why is this nice? Why did I want a -4 here? Right, that's why we did this. We did this particular row operation where we multiplied row 1 by -4 in order to make the coefficient of y -4 here. Why is that a nice thing?
You can get rid of the y's.
Because now if I add row 1 and row 2, and the notation for this would look like this. My new row 1 is going to be my old row 1 plus my old row 2. All right, so new row 1 is old row 1 plus old row 2. I'm adding one row to another row. Row 1 is the only row that's going to change here. So row 2, again, I just copy down 3x plus 4y equals 14. 3x plus -8x is -5x. 4y plus -4y is, all right, 0y. And 14 plus -4 is +10. And this is nice because that first equation says -5x equals 10. I've gotten rid of all the y's in that first equation, which means x is 10 divided by -5, x is -2. So we succeeded in eliminating the y's from the first equation. And that gave me an equation just involving x, which I could solve. Finally, we back substitute or back sub x equals -2 into any of these equations. Any equation with a y and solve for y. So for example, I could back substitute into the original equation 1, or I could back substitute into the original equation 2, or I could back substitute into the modified equation 1 here. Any of them would be fine. Let me just go back to the original equation 1. So that's 2x plus y equals 1, which would become, if x is -2, 2 times -2 plus y equals 1, or -4 plus y equals 1. And adding 4, we get y equals 5. So that's it. Now we're done. Therefore, the solution is the ordered pair -2, 5. In other words, if I wanted to know where those two lines cross, they cross at the point -2, 5. This is elimination. And for a 2x2, you notice it takes up about the same amount of space as substitution did, right? If you ignore all the instructions that I wrote over here, this takes maybe even a little less space than substitution did. It's very efficient. And more importantly, this generalizes to larger systems. If you have a big system like a 3x3, 4x4, 5x5, elimination is the only way to go. You could, in theory, use substitution, but it's very, very easy to get into trouble. It gets incredibly messy. As the systems get bigger and bigger, substitution gets harder and harder. Elimination stays the same, does not get harder with bigger systems. In some ways, it gets easier.
Can I ask a question?
Of course.
When you were using the graph and the substitution method, we got a 3, 1.
Mhm.
And then with the elimination, we got -2, 5.
Different systems. Yeah, different systems.
Was it because we had changed?
Yeah, so in these first two examples, the system I was solving was 2x minus y equals 5, x plus 4y equals 7. The system we were solving here was 2x plus y equals 1, 3x plus 4y equals 14. So we're solving
Oh.
two different systems.
Okay, sorry. Never mind. I didn't even catch that.
No worries. Yeah, if we used elimination on that same system, we would have gotten the same point.
Okay, sorry. That was my bad.
No worries. Okay, we're going to get more practice with elimination in just a minute. Before I do that, I want to think with you a little bit about the possible solution cases. So this is a theorem. All linear systems fall into one of the following categories. It's possible that there is a unique solution. Right? Like the two systems we've seen so far, each had a unique solution. There's one point that solves the system. It's also possible that there is no solution. And then the final possibility is that there are infinitely many solutions. And in the 2x2 case, you can think about each one of these having a corresponding picture. The unique solution case is where you've got, two lines with different slopes. And then you've got just one solution. No solution. Well, if you have two parallel lines with different y-intercepts, those two lines will never touch, which means there's no solution. And then the infinitely many solutions case, this is where you have two parallel lines that are actually the same line. Meaning every point on the line is a solution. I'll show you that elimination process will reveal to you which of these three cases you're in. If you have a unique solution, then the elimination process will just find you that solution. If you have no solution, then the elimination process will lead to a contradiction, something like 0 equals 1. And if you have infinitely many solutions, the elimination process will lead to something called a tautology, a statement which is true independent of the values of the variables. In the unique solution case, all you're expected to do is find that point. In the no solution case, you just tell me there's no solution. In the infinitely many solutions case, you've got more work to do. You need to tell me that there are infinitely many solutions, but notice not every point in the plane is a solution, right? Like if I take a point over here that's not on that line, this would not be a solution to that system. So you need to somehow describe to me the set of all ordered pairs that solve the system in case 3 here. And that can take a little bit of work. So I'll show you how to do that. But first, I just want to get a bit more practice with elimination. So we're going to do one more nice problem, and then we'll look at the two kind of odd cases. So let's look at one more kind of nice problem. Let's solve the system 3x plus 2y equals 14 and x minus 2y equals 2 by elimination. All right. Anybody make a suggestion as to a good first row operation to perform on this system?
Could we multiply the second row by 3 or -3?
Certainly we could. Yeah, we can multiply the second row by -3. Let's go ahead and do that. It's not the only thing we could do, just to be clear.
Isn't it already good to solve by elimination because of those y's right there?
Yeah, and I think that's definitely the faster path here. So it's true that if I make this a -3x, then add to the first row, the x's will go away. But also, I've got a positive 2y here and a negative 2y here. So I think the faster path would be to just add the rows. So I can make my new row 2, say, equal to old row 2 plus old row 1. So row 1 I'll leave alone, 3x plus 2y equals 14. And then my new row 2 is going to be what I get by taking my old row 2 and adding row 1 to it. So x plus 3x, that's going to be 4x. Negative 2y plus positive 2y is plus 0y. And 14 plus 2 is 16. Now, equation 2 says 4x equals 16, which means x has to be 16 over 4, which is 4. And back substituting this, and you could back sub into either of the original equations. Let me back substitute into the original equation 2. I'll write it down first, just x minus 2y equals 2. This will become 4 minus 2y equals 2. Subtracting the 4, I get negative 2y equals 2 minus 4 is negative 2. Dividing by negative 2, I get y equals 1. Easy breezy. And I think we would all agree this right here, this whole procedure is super duper simple, very, very fast, much faster than substitution would have been. So the solution is the ordered pair 4, 1. Done. And you're right that we could have eliminated the x's instead. And we would get the same solution if we eliminated the x's instead. It's also true that once I get to this stage where I have x, I could have plugged back into equation 1 or equation 2. It doesn't matter. Would have gotten the same thing either way. Any questions on this? All right, let's try one more. Oh, actually, that's two nice clean elimination problems in a row. Let's jump to something a little strange. So let's solve 8x minus 6y equals 15. I'm sorry, 8x. Minus 2y equals 5. Getting ahead of myself. And negative 12x plus 3y equals 7 by elimination. So I want to pick a variable to eliminate from one of these equations. I can try to get rid of the x's here or try to get rid of the y's here. Doesn't matter.
Are you able to multiply both?
We can do, let's do separate row operations for each, just to take everything one step at a time.
So could you multiply the first by -3 and the second by -2?
Good, let's multiply. So my new row 1 will be -3 times my old row 1. So -3 times 8 is -24. So I'll have -24x. -3 times -2 is +6y. And -3 times 5 is -15. And the second row, I'm not doing anything to right now. I'll just leave it as -12x plus 3y equals 7. Then for my second row operation, I'll multiply row 2 by +2, right? Because that will turn the 12 into the 24. So my new row 2 will be 2 times my old row 2. Row 1 stays the same, -24x plus 6y equals -15. 2 times -12x. Actually, let me make this a -2, right? And give them opposite signs. So that would become +24x, and then minus 6y equals -14. So for my second row operation, I'm going to multiply row 2 by -2. And now if I add row 1 and row 2, and it doesn't matter which one you're thinking of as being the result. Let me say my new row 2 is old row 2 plus old row 1. Leave row 1 alone. I get -24x plus 6y equals -15. But over here now, -24x plus +24x is 0x. +6y plus -6y is 0y. And -15 plus -14 is -29. And this is a problem because now equation 2 says 0x plus 0y equals negative 29. And 0x is 0, always. 0y is 0, always. And this says 0 equals negative 29, which is a contradiction. 0 is not equal to negative 29. This is a statement which is untrue no matter the values of x and y. There is no numbers x or y you can plug into this to get a true statement. 0 will never be equal to negative 29. So assuming a solution exists, we run through this procedure to find the solution, and we arrive at a contradiction. I don't know if anybody still reads Ayn Rand. She's become very unfashionable lately, and I totally understand why. She's terrible in a lot of ways. But if you arrive at A and negative A, you need to examine your hypotheses. Yeah, so let's see questions in chat that I didn't get either earlier. Yeah, you can multiply each row by any number you want. I prefer to think of them as separate steps because that way you can kind of keep track, right? You can go back one step at a time and follow what we did. So I recommend only doing one row operation at a time, but certainly we can multiply row 1 by any number we want, and we can multiply row 2 by any number we want. So you can, in the end, get the result that you would get by multiplying row 1 by negative 3 and row 2 by negative 2. No harm there. So if you arrive at something that's impossible, there must have been an incorrect assumption made. And the incorrect assumption here was that a solution existed. So when you arrive at a contradiction, this means there's no solution to the system. Those lines never touch. They have the same slope, but different y-intercepts. All right, this first line is a line with slope 4 and y-intercept 5/2. This second line is a line with slope 4 and y-intercept negative 7/3. Or sorry, positive 7/3. Yeah. So same slope, different y-intercept. These are parallel but distinct lines. So they'll never touch. There is no solution. And by running through this process, we arrive at a contradiction. And that's what tells us that there is no solution.
Would you only have to do that once? You don't have to sit there and keep trying to figure out if something does work.
Yeah, that's correct. Once you get here, you're done. You get here, you say, oh, this is a contradiction, therefore there's no solution and there's nothing more to be done. There's no other work that we could do to hope to find a solution because we know for sure at this point that no solution exists.
Okay.
And the picture here, if we can draw it. That would be y equals 4x minus 5/2. So equation 1. Equation 1 looks something like this. And equation 2 would be 4x, 4x plus 7/3. And these guys, they'll never touch. They're parallel lines. That's correct, Megan. If we'd chosen to eliminate the x's instead, or however we want to think about it, what happened here is that we ended up eliminating both variables at once. All right, so if you eliminate both variables at once, but this right-hand side is not 0, then you know you have no solution because you've got 0 equals something other than 0. And the kind of one of the things we're going to see is that if both variables get eliminated at once, then you're in one of those two weird situations. Either you have no solution or infinitely many solutions. If both of these go away at once and this is not 0, then no solution. If both of these go away at once and this is 0, what we'll see is that means there's infinitely many solutions, but we'll see that in just a sec. And it's true that there are other ways we could have gone about eliminating here. I think we thought of it like we're trying to target the x's, but we ended up targeting the y's at the same time. But we could have thought of it like we're going to target the y's, and it would have turned out that we killed the x's at the same time. Okay. Let me check the time, see how we're doing. Oh, we are a little bit over time, aren't we? All right, let's get through this last example. All right, and of course, by elimination. So again, I want to pick a variable to try and eliminate. Let's say I'm going to try to eliminate the x's. So if I multiply through row 1 by 4, and I multiply through row 2 by -3, then what will I get? Well, 4 times row 1, that's 12x minus 24y equals 48. And -3 times row 2 is going to be -12x plus 24y equals -48. And now if I add rows 1 and 2 together, say my new row 2 is old row 2 plus old row 1, then row 1 stays 12x minus 24y equals 48. Row 2 will become 12x plus -12x is 0x. -24y plus +24y is 0y. And +48 plus -48 is 0. So now equation 2 says zero x plus 0y equals 0. In other words, says 0 equals 0. And this is called a tautology. Statement, which is always true. And this tells me there are infinitely many solutions. But we're not done. What are the solutions? Just because there's infinitely many of them does not mean it's not true that any ordered pair XY is a solution. For example, zero comma zero is not a solution to the system. Right? If you plug in 0 for X and 0 for Y, this would say 0 equals 12, and this would say 0 equals 16. Neither of those are true. So once you get to this infinitely many solutions, once you arrive at a tautology, something like 0 equals 0 or 1 equals 1, it'll always be 0 equals 0. Once you discover that there are infinitely many solutions, you still need to tell me what those solutions are. And the way we do this, what is true, is that for any number X, we can find a corresponding Y value such that X comma Y is a solution. And there's two different notations for this. Unfortunately, your homework uses both. So what we do here is we let X equal T be a free variable and solve for Y in terms of X. And since what I really know, the fact that we have infinitely many solutions means these are both the same line. I can plug in, I can solve either one of these for Y in terms of X to get my guy. So say that first equation, 3x minus 6y equals 12. That would be 3t minus 6y equals 12, which would mean negative 6y equals 12 minus 3t. And then I can divide both sides by negative 6, and I get y equals 12 divided by negative 6 is negative 2. Negative 3 divided by negative 6 is positive 1/2. So this is your solution. We would wrap up here by saying, i.e., any ordered pair of the form t comma negative 2 plus 1/2 t is a solution. Sometimes they will have you just leave x as x, right? And so we would have y equals negative 2 plus 1/2 x. Other times they'll say let x equal t and solve for y in terms of that. It's unfortunate that your book uses both notations. This is the more common one. And this is how we would finish the problem here. We would say that our solution is all ordered pairs of this form. All right, we did not get to look at any 3x3s or larger systems today. So in the video lecture that I'm going to post for you guys on Thursday, we will solve 3x3 systems using elimination. Thankfully, it's the same sort of thing. And I will give you an algorithm called Gauss-Jordan elimination, kind of a procedure that always works, because it's possible if you're trying to eliminate one variable that you end up undoing some elimination that you've done elsewhere. So we want a kind of procedure that is very algorithmic, and I will show that to you. And we will also start talking about matrices, which are a nice way of working with linear systems where you just don't write the variables, you only write the numbers. And it just saves you some ink and some paper, and it makes life a little easier. Also, study of matrices will lead to a study of matrix algebra, which is a really beautiful thing that I'll show you as much of as we can before the term ends. But yeah, that's it for today. I got to run. I got another class right now. I know that you wanted to talk at the end of class here, but since we are right at the edge of time, I'll ask you if you could just send me an email. That would be nice. And we can either talk in office hours or keep the correspondence between email. That's it from me, guys. I'll see you in the video on Thursday.